So we have now set up these two coupled mass balance equations. And what we're going to do in this coming section is look at the solution to these near field, far field equations. I'm not going to derive these equations, but just present the solutions as they are. And so in this slide, I'm going to show you the solution to the coupled differential equations that result from the mass balance equations I showed in the previous slide. And as you can see, these are very complicated looking and frankly ugly looking, but we can make some sense out of it by considering each one of these terms. So now let's look at the near field equations, and the first two terms are just constants. So the C near field is equal to G over Q plus G over beta. If you recall, in the well-mixed room model equation, in the steady state, the concentration in the room became G over Q. So that is the concentration at all points in the room. But now that we have broken up the room into a near field and a far field, we expect that the near field concentration is going to be greater than G over Q once you reach steady state. So now we have two terms, so G over Q plus an additional term, G over beta. Now let's look at the terms that have some time variation in them. So both of these terms, so G times a big constant term times an exponential term. And so the exponent in both of these is a function of these constants lambda 1 and lambda 2. And the expressions for lambda 1 and lambda 2 are given at the bottom of this slide. It may not be intuitively obvious when we look at these two equations, but it turns out that for realistic values of beta and q, both lambda 1 and lambda 2 turn out to be negative numbers. And so when we come back to the near field equation, this exponent of lambda 1 times t is really an exponentially decaying term. And the same thing is true for exponent of lambda 2 times t. So both of these time varying terms in the near field are exponentially decaying terms, although decaying at different rates. So we can think about this and say, okay, what will happen in the steady state, meaning what will happen after a long time has elapsed? So both the time varying terms will asymptotically go down to zero. And what we are left at this steady state is a near field concentration of G over Q plus G over beta. The other two terms go down to zero. Now let's think in a similar way about the far field. So C far field is there's a G over Q, which is a constant, and then these two more complicated looking terms, but they are both also multiplied by these exponentially decaying terms, exponent of lambda 1 times t and exponent of lambda 2 times t. And so in the steady state, both of these terms will also vanish. And so in the steady state, the C far field will reach an asymptotic value of G over Q. It is important to note at this point that in the steady state, the far field concentration, which is G over Q, is exactly the same as the well-mixed room steady state prediction, which is also G over Q. So what this means is, in the steady state, both the far field and the well-mixed room give you the same result, but the near field gives you a concentration that is greater than just G over Q by an additional amount, G over beta. So to recap, the steady state concentration equations for the near field and far field are as shown in this slide. For the near field at steady state, the concentration is G over Q plus G over beta. And in the far field, the steady state equation is given by G over Q. And as we can see, the near field concentration is greater than the far field concentration, which makes sense because the worker is closer to the source. We can make a few more remarks about these two steady state equations and some of their implications. So if beta were exactly equal to Q, then we can look at these two equations and say that the near field concentration is 2 times the far field concentration. If beta now, by the same token, is less than Q, it would therefore mean that the far field concentration is greater than 2 times the far field concentration. And this is most often the case in a room with low airspeed near the source, or in a large room with a large general ventilation rate, or Q. So the near field concentration is typically much greater than the far field concentration. In general, Q increases relative to beta as the room size increases. And so when that happens, the model will predict a relatively higher exposure intensity near the emission source compared to the well-mixed room model. And what this means is the well-mixed room model leads to more substantially underestimating exposure near the source as the room size and Q increases. We can look at these two equations and do some example calculations. So in this example, we will assume that the generation rate G is constant at 105 milligrams per minute. The volume of the far field is 240 cubic meters. The volume of the near field is 1.1 cubic meters. The airflow rate through the room, Q, is 15 cubic meters per minute, and the interzonal airflow rate, or the airflow rate between the near field and the far field, is 7.25 cubic meters per minute. Now, if we plug these values into the equations for the near field and far field, we'll get these two time trends. And you can see that in the far field, the concentration at steady state is just G divided by Q. So 105 divided by 15, or 7 milligrams per cubic meter. And so in the near field, the concentration at steady state is G over Q, so that's 105 divided by 15, plus G over beta, so 105 divided by 7.25. And so we'll get a near field concentration somewhere around 22 milligrams per cubic meter. We also can see that the near field concentration in the very beginning, at time t close to 0, there is an initial sharp jump, and then it starts increasing. But the same thing is not true for the far field, where you have a more gradual increase. But the rates at which these two concentrations increase are given by lambda 1 and lambda 2.